Hello everyone, this is this week's highlight video. Let's go ahead and start with the ideal gas law. PV equals NKT. Here P is pressure in pascals, V is volume of the gas in meter cubed, N is the number of molecules in the gas, K is this Boltzmann's constant, last T is temperature. Now this Boltzmann's constant, this is just kind of like a unit conversion. So that's what I want you to think about it as. So we as scientists chose how long a meter was, what the definition of a Kelvin was. And so because of those definitions that we chose for those units, this is going to convert between the two, between pascals, meter cubed, Kelvin, and number of molecules, okay? And the value here is 1.38 times 10 to the negative 23rd. So for instance, I have this piston that is compressing this gas here. Now it's compressed it down to a volume of 0.03 meter cubed, and there are 2.5 times 10 to the 24th molecules that are inside the gas here. The temperature of the gas is now at 350 Kelvin, so what's the pressure in the gas? We can use the ideal gas law, PV equals NKT. We're told that the volume is 0.03, the number of molecules, we know Boltzmann's constant, this is just this number, and the temperature is 350 Kelvin. We can divide 0.03 to both sides and solve this, and we arrive at 402.5 thousand pascals, or 402.5 kilopascals. So here's another situation. It's the same idea about the gas and a piston. Now, here we have this lead shot. This is just, essentially it's just this weight that's on top of this gas that's kind of holding it down, keeping it compressed. The walls are insulated, so there's going to be no heat transfer this direction, but there is a big thermal reservoir here in the bottom. And we can choose what that temperature is going to be. So we can turn it higher or colder. And that's going to maintain the temperature of the gas based on what temperature we choose this reservoir at the bottom to be. So here it's held at this constant temperature T that we chose, and more weights, we're going to add more lead shot into this little bucket here. What that's going to do is it's going to cause the piston to lower. It's going to lower the piston down. And the question is, how will the pressure in the container change? So we're going to look at a couple of things here. First of all, we want to know what pressure is. Now, the volume is also going to get smaller. Now, the number of molecules, that's not changing. It's all enclosed here, so the number of molecules that's are not going to change. Boltzmann constant's not going to change, and the temperature is also not going to change because of the thermal reservoir here. So these three quantities are not going to change. So if I decrease the volume, if I make the volume smaller, what must the pressure be doing? Well, this side is not going to change. So if V gets smaller, the pressure must get larger in order to keep this the same. And so that's another way that we can look at this without numbers, just thinking about conceptually how these numbers are changing or are not changing. Next is the first law of thermodynamics. And to start, we'll do a little bit of reminders from last week. So temperature is another tool we use to measure the energy of an object or fluid. Now, when I say fluid, that means gas and liquid. They're both fluids. And Q, that's the transfer of this heat energy we talked about. And there are two types. Q equals mc delta T. This is when you're heating or cooling an object outside of its transition zones. So you're not making it into gas or you're not making it into a solid. And then Q equals ml. This is when you're going into phase change. So, liquid to solid and liquid to gas and so on. Also, work is the transfer of energy from one form to another. So work is force parallel times the distance that the object travels. Now, remember, all temperature is just another tool we use to measure the energy. Now, we're going to call the energy that is in the temperature E internal. So this is the internal energy. This is that kinetic energy and potential energy that's stored inside this object or fluid. And with that, we arrive at the first law of thermodynamics, that the change in the internal energy of an object or fluid is equal to Q minus W. So again, Q, this is the heat energy added to the object, and this is the work done by the object or fluid, okay? So as we add heat to it, the object can do work on its surroundings. And these combined will tell us how the internal energy of the object or fluid is going to change. So back to this, okay? So it's getting held down by this lead shot weight, and we're going to remove some of the weight here. So we're going to take some of this lead shot out. When we do, the gas pressure here is going to push this piston up a little higher before it comes to rest again. So is the work done by the gas positive or negative? Well, the force from the gas onto the piston is upwards, and the piston is going to be moving upwards. So those are both in the same direction. So therefore, the work is going to be positive. So positive work because the force and direction are both in the same direction. Now, if the gas does 13 joules of work, so as the gas pushes the piston up after we remove some of the weight, the gas has done 13 joules of work onto the piston here. And when this happens, the thermal reservoir has added 25 joules of energy to the gas. So that's the Q, right? This is this heat energy. So as this expanded upwards, the thermal reservoir added 25 joules of energy to the gas. What is the change in the internal energy of the gas? Well, we can just use the first law of thermodynamics. The change in internal energy is Q minus W. I told you that Q is 25 joules. That's the thermal energy from the reservoir. Minus 13 because the gas actually did work while it expanded. And so we can subtract those two so that the gas has gained an internal energy of 12 joules during this process. Another way to think about these kind of transitions is with a pressure versus volume plot. So here on the vertical axis, we have pressure, and in the horizontal axis, we have volume. So let's say we start at some certain pressure and volume at point A, and then we change the pressure and volume to a different condition, point B. Now we do this with this arrow here. So you see along this arrow, the pressure is maintaining the same constant value. And the area here, the area under this graph, this is the mechanical work that the gas is doing. So the area under a pressure versus volume graph is the mechanical work that the gas is doing. And mechanical work is kind of what we're interested in because we eventually want to use this as an engine, a source of energy. We want to use it to do work on things. The temperature will also change while we're doing this. And heat energy will also be exchanged. So there's two things that this is not showing. It's not showing how the temperature changes, and it's not showing how much heat energy goes into it. But from this plot, we can figure out how much mechanical work we're getting out of it. Arrows pointed in the rightward direction mean that we're going to be getting positive mechanical work out, and arrows pointing in the leftward direction means that we have to do mechanical work onto the system in order for that transition to happen, in order for us to move a certain direction in the pressure versus volume graph. Now, the shape won't always be simple. This is a simple rectangle here. Sometimes it will be, but sometimes it won't. I'll show you some of those now. So this first one is called a very fancy, sciencey term, isobaric. Right? This is when the pressure remains constant. So for this graph, is this doing positive work, zero work, or negative mechanical work? Well, the arrow is in the rightward direction, so that means it's doing positive mechanical work. Okay. Another one is isochoric. So there's going to be a lot of these sciencey terms. This is when the volume remains constant. So if we look here from A to B, you see that the volume is the same value down here. So the volume has not changed. So this is in isochoric transition. What about this one? For this graph, is the gas doing positive, zero, or negative mechanical work? Well, the work is the area under the graph, but there's no area there, right? There's no area to be had. So this does zero mechanical work because the area under this graph is zero. Isothermal, okay? This is when the temperature remains constant. So this is the only process on a pressure versus volume graph where the temperature of the gas will remain constant. But we got to be careful. This doesn't mean that heat energy isn't added or removed from the system, okay? So if the temperature remains constant, the internal energy is not changing, right? The internal energy is not changing if the temperature remains constant. But if you look under the graph here, there's an area, which means there's work done. So in order for the change in internal energy to be zero, the temperature is not changing, the gas is doing mechanical work, we must have added or removed heat energy from the system, depending on which direction we go, okay? So just because isothermal, you may think, oh, the temperature's not changing, therefore no heat energy is added or removed. That's not the case. The case is true for this next one, which I'll tell you in a second. As an example, when pressurizing a scuba tank, they'll put it in a big bucket of water to try to keep it from getting too hot, to try to maintain the temperatures. This is where they're trying to make it an isothermal process when they're adding air to a scuba tank. For this graph, is this gas doing positive, zero, or negative mechanical work? Well, the arrow is in the leftward direction. So in this case, this gas is doing negative mechanical work during this transition. All right, here's the other one that I was hinting at. Again, this is isothermal. That's this graph here from A to B. There's also another term, adiabatic, okay, from this lower curve here. This is where no external heat energy is transferred. So that means that if no heat energy is transferred, you see how there's still work done? There's still an area under the graph, which means that if Q is 0 and W is not 0, then the change in internal energy of our system is going to change. So the temperature is going to change. So you may think, oh, no external heat energy transfer. That means that there's no temperature change, but it's not true. In an adiabatic transition, because there's work and no Q, the internal energy will still change. So the temperature of the gas will still change. Now, for this graph, is this gas doing positive, 0, or negative mechanical work? Well, the arrows are in the rightward direction, so it's doing positive mechanical work. All right, now for an engine, we want to repeat this process. So we don't want to go just from A to B. We got to get back to A somehow in order to repeat the process over and over again. So let's start here. If we go from A to B, we're going to get a lot of mechanical work here, okay? So there's an area under the graph. It's to the right, so the gas is doing positive mechanical work. This is an isobaric because the pressure is not changing. So we're going to gain 50 joules of work from the system, okay? Now, we want to get back to A. If we just go straight back to the left, then we're going to lose 50 joules of mechanical work because that's how much work we have to do back on it to go from B to A. But we're going to do something different. We're first going to go downwards from B to C, isochoric because the volume is not changing. So no work is done here, like we mentioned before, there's no area. Then we're going to go from C to D, another isobaric transition. Now, because we're lower, do you see how this blue is smaller than the full rectangle that we had before? So because this is smaller, we only have to do 30 joules of work on the system from transition from C to D. And finally, we're going to go from D to A, isochoric again. No work is done. So we gained 50 joules going from A to B, nothing from B to C. We lost 30 joules from C to D, and then nothing from D to A, meaning that we have gained 20 joules of mechanical work going from A, B, C, and D. And we can keep doing this over and over again to gain that much work every time we do this process. Now, when we go clockwise, positive work is going to be done by the gas. And if we go counterclockwise, negative work is going to be done by the gas. Any loop will do mechanical work, so not just that rectangular one. There's any kind of different shape will do it. What about this loop? Is this loop producing positive, negative mechanical work? Well, it's going counterclockwise, which means it's doing negative mechanical work. Okay. You may be thinking to yourself, oh, why would you ever want to do that? Well, this graph doesn't show everything. Remember, there's heat energy that is involved and the temperature of the gas, which is involved. Air compressors use counterclockwise loops to keep your home cool or your refrigerator cool. Mechanical work is inputted into the system, which pulls heat energy out of its surroundings in order to cool things down. So when you want to cool things down, we want to go counterclockwise. And typically, when you want to use it to an engine or sorts, we're going to be clockwise to gain mechanical work out of the system. All right, here's the review slide. We started with the ideal gas law, P equals NKT. We transitioned to the first law of thermodynamics. The internal energy is equal to Q minus the work done by the fluid or object. A bunch of different sciencey terms. Isobaric when the pressure is constant. Isochoric when the volume is constant. Isothermal when the temperature is the same, but heat energy is added or removed. And adiabatic when no heat energy is added or removed, but the temperature will change. And we want to have loops for generators or refrigerators. All right, that's it for the highlights for this week. Hope that helps.